Okay. So good morning, everybody. Thank you for joining us very early in the morning, especially in the UK, in this IEEE Virtual Distinguished Lecture by prestigious Professor Bruno Clerc. This virtual distinguished lecture is co-organized by UK, Ireland, and Spanish IEEE chapters. Here with me, there is Professor Nauman Aslan, the UK and Ireland chapter chair, and I am Victor Hill, the Spanish chapter chair. First, we would like to thank Professor Clerc for accepting our invitation for giving us this distinguished lecture. It is an honor to have you here. The curricula of Professor Clerc is impressive. I will try to make a small summary in order to not delay too much the talk. Bruno Clerc is a full professor, the head of the Wireless Communication and Signal Processing Lab, and the deputy head of the Communication and Signal Processing Group within the Electrical and Electronic Engineering Department at Imperial College in London, even though now it's in South Korea as research stay. And this is why we have scheduled this talk very early in the morning, because in South Korea is late in the afternoon. Bruno has actively contributed to 4G, the LTE and IEEE 802.16m standards. He has authored 2 books of MIMO wireless communication and MIMO wireless network, 250 international research papers, and 150 standard contributions. Besides, he's the inventor of 80 issues or pending patents. He serves as an editor for the main communication IEEE journals like Transactional Communication, Transactional Wireless Communication, Signal Processing. He received the prestigious Blondie Medal in 2021 from France for the exceptional works contributing to the progress of science, and the Electrical and Electronic Industries and the EURASIP Best Paper Award in 2022. He is fellow for the IEEE. So thank you very much. The floor is yours.
Thank you very much, Victor and Nauman, for your very kind introduction. It's a pleasure to be here today. So let me share my screen. Right. So I hope see it by now. Right. So today I will be talking about satellite communication, and this is a relatively new topic for me, in the sense that I've been working on wireless communication and communication theory for many years. But a lot of the tools that actually we're looking at there are applicable to satellite communication. And interestingly, I did my master's degree on satellite communication 20 years ago, but then I stopped working on the topic. And in the past few years, things have changed quite a bit. And there's been a lot of interest in this topic. And I know, for instance, in Spain, there are many groups working on that. As well as actually in the UK. So today we're going to look at not all satellite communications, but specifically some emerging multi-antenna and multi-user signal processing. I have to thank my PhD student, Long Fei Yin, who has been who's doing her PhD on this topic of satellite communication. And many of the results that I will present actually come from her PhD work. So let's look at the outline. So this is what I will be talking about. I will briefly introduce satellite communication. Then I will look at multi-antenna and multi-user processing and briefly review some of the typical multiple access techniques that are used in modern systems or in the current literature, and how this could be used in satellite. And then I will dig into 3 really technical parts related to satellite. I will look at multibeam satellite systems and study how different multiple access and multi-user processing can be used. I will look at multi-gateway, multi-beam satellite, and then I will look at the integration of satellite and terrestrial systems. And finally, before concluding, I will look a bit at the physical layer design and how much performance gain can we get once we really look at the actual physical layer implementation and link level simulations. So satellite has drawn quite a bit of attention in the past few years and is perceived as something quite important for beyond 5G. And there are three reasons for this. The first one is to enhance the user experience by providing actually a better network reliability and some form of continuity of the service for a lot of different type of devices. Could be IoT device, could be passengers on board of actually moving platforms and so on. The second role or benefit of satellite is to enhance the coverage and to provide ultimately a service ubiquity to all areas that actually not served or not much served by the current terrestrial networks. So this is the unserved areas like for deserts, oceans, forests, and so on, or the underserved areas that you have typical rural areas in some part of the Earth. And the third role of satellite is to provide multicast and broadcast opportunities. And this is very relevant when we think about service scalability. When the number of actually users or device grows significantly, we can really leverage the multicasting and broadcasting opportunities of satellite over a very wide area. So the use case of satellite communications are quite numerous, whether we talk about in urban area, rural areas, or remote areas. And I listed here a few of them coming from this paper, ranging from IoT connectivity to, for instance, drones or backhaul or broadcasting popular content, connected cars, disaster relief, broadcasting of media, again, backhauling, but not in rural areas, direct connectivity. This is very classical, something that has been existing for quite a long time, but new application like tracking, and then all those forms of communications to remote areas and typically those moving platforms. Right, so there are different types of satellites and the most popular one are the GEO, MEO, and LEO. So the geostationary, the medium Earth orbit, and the low Earth orbit. And the difference between them is essentially the altitude range. So the GEO, they stand at 36,000 kilometers above Earth, and the MEO and LEO are actually much lower. So that means actually the orbital period of those different satellites differ quite a bit from each other. So the GEO is obviously 24 hours. This is actually stationary with respect to Earth, but the LEO can go around the Earth in pretty quickly in 10 to 40 minutes. So this leads to a number of changes or a number of challenges as well. For instance, the number of handoff in GEO is none, essentially, since the GEO is always stationary. But the LEO, since it's moving really fast, the handoff is something that is a pretty important issue to consider. And then those different satellite systems have used over the years a different spectrum. I think they started many years ago with the low bands like the S and C, and it has moved towards higher bands in the more recent years. And nowadays the KU and Ka bands are very popular, even though those bands have been discussed already 20 years ago. So I remember when I was doing my master thesis, we were already working on Ka band for satellite communication. But I think the whole evolution satellite has taken a bit more time than this whole millimeter wave business in cellular systems. So nowadays we're really looking at KU to Ka bands for satellite applications. Right. So this is a very simplistic representation of a satellite systems where we have a few different links here. So we have a gateway, a satellite, and we have user terminals. And so this link from the gateway all the way to the user terminal is called the forward link, and is made of two parts: a feeder link between the gateway and the satellite, and then the user link between the satellite and those user terminals. And then the reverse link is called the return link, that goes from the user terminals all the way back to the gateway. You can see here on the ground on Earth, the satellites forms multiple beams. And so this is what is called multi-beam satellite system. And in each of those beams, essentially the satellite may serve one or multiple users at once. So this is what this multi-beam system looks like. So essentially what we have is we have a bunch of reflectors and a bunch of antenna feeds. And the antenna feeds, essentially what they do is they radiate electromagnetic waves, so they illuminate the reflector, and the reflector reflects this electromagnetic wave and creates on the Earth, essentially, those spot beams. And those reflectors and the antenna feed are designed such that those different spot beams have a relatively good isolation with each other, though in practice, you can imagine that there is still quite a bit of interference between those different beams. And so here it's an example here with four color codes, and I will explain this a bit later on, but essentially it could mean, for instance, that those four colors refers to four different frequencies. And so in this case, you see the blue frequencies and the red frequency will not interfere much with each other, because essentially you form some form of orthogonal multiple access. So you have some form of orthogonality between frequencies and between the beams here. But you could imagine also that all those beams operate on the same frequencies, and then in that case, you're going to have quite high interference between those different beams. And that's the reason why in modern satellite systems, like you have in those DVB S2X, for instance, standards, additionally, you have some form of precoding that is applied at those antenna feeds. And precoding is there to manage the multi-beam interference. So in this figure here, we have essentially 8 antenna feeds here. That creates 8 beams. And this is a little bit reminiscent of 8 transmit antenna system in a cellular system, where you can do some form of precoding across those 8 antennas. Here, equivalently, we can do precoding across those 8 antenna feeds to manage the multi-beam interference. And we'll look at this in a minute. What are the practical challenges in satellite communication? How does it differ a bit from cellular systems? So the first one is that if you tend to increase the frequency reuse across those multiple spot beams, so if all those beams here use the same frequencies, you have a lot of interbeam interference. And this is something that can be quite severe and that needs to be managed very efficiently. The second challenge is the frame-based precoding that we have in satellites. And so what that means is that when you have multiple users in a beam here, what happens is that modern satellite systems, they encode the packets of all those 3 users in the beam, they encode those 3 packets into one encoded code words. And so effectively what it looks like one code word has to be received by those 3 users. So it looks like a multicast transmission, but because we have multiple beam, is essentially a form of multi-group, multicast transmission from a physical layer perspective. And this is a little bit different from what we have in cellular networks, where we are more used to have unicast-based transmissions. So the code word, the packet of a given user is encoded in a code word that is only decoded by a given user. Here it's a bit different because those packets are encoded jointly into one code word. And the reason for this is really to try to get longer code words that are actually more robust to noise, so more longer and use essentially code words that are longer so that we can increase the coding gain of the error correcting codes and therefore be more robust to noise. And this is particularly important when you have really large path loss as we have in satellite communications. Another issue is the per feed power constraint. So in cellular communication, we often look at some power constraint. Here, satellite engineers, they're more interested in per feed power constraint because obviously the power available at the satellite is extremely limited and you don't want to waste it. So you want to make use of the power amplifiers very efficiently at the satellite. The satellite channel is also different from the classical cellular or terrestrial channels, where we are subject to much more line of sight. So we don't have lots of bit scattering, so we don't really model things like using relay fading. We have atmospheric fading that is slowly fading, and we have a very large path loss. We have also the problem of imperfect channel state information at the transmitter. This is something that we have also in cellular system. But here it's slightly different, and it's due to latency and mobility. So if you have latency, is very severe when you have geostationary, because the round-trip delay, as you can see, is about 500 milliseconds, which would be much longer than what we have in cellular systems. It would be shorter for LEO systems, but the LEO systems, they move very, very quickly. So this combination of latency and mobility would lead to quite significant imperfect knowledge of the CSI at the transmitter, at the satellite, and therefore at the gateway. And then we can have high Doppler, especially when you have low Earth orbit satellites. And the last difference is the overloaded regime. So the number of users that are served by a satellite is typically much larger than the number of beams, or the number of effective antenna feeds that the satellite has. And in this case here, if each of those beams has to serve 3 users, essentially indeed the system becomes overloaded because we have 3 times more users than the number of antenna feeds. So this can be quite different from cellular systems, where we typically operate in an underloaded regime when the number of transmit antennas is actually larger than the number of users. And this is what we have, for instance, in massive MIMO in terrestrial systems. So, those satellite systems are inherently multi-user systems, and the big question is how to serve those multi-user systems. And so this is where we have lots of, obviously, connections with communication theoretic problems. We're going to look at here this forward link of a satellite system from the gateway all the way to those user terminals. And we're going to be inspired by communication theoretic problems that we have in cellular systems. For instance, when we have the downlink of a cellular system, and we have typically what is called a broadcast channels in information theory. So this is what we're going to look at in this talk. So how can we serve those different users? Well, the first way we can think of is obviously use some form of orthogonality and serve users onto different beams with different frequencies, using, for instance, FDMA, right? And this is very popular in 2G in cellular systems, but it's been used in cellular systems in satellite systems quite a bit. This is the examples of the four color frequency reuse that I showed you earlier on, where you divide all your beams into 4 colors, and each color is assigned a different frequencies. And so by doing so, you decrease the interbeam interference that you have in the systems. But obviously, this has a lot in terms of spectral efficiency as well. And nowadays, those systems try to move away from 4-color frequency reuse, but go more towards a frequency reuse factor of 1. The other approach is to do some form of multi-user precoding to manage this interbeam interference. And this is reminiscent of what we know in cellular systems, space division multiple access, where you use the spatial domains and so the precoding to essentially manage the multi-user interference. And this has been used extensively in 4G and 5G, and is used in DVB-S2X. So the way it works is that you imagine that you have, for instance, K messages intended for K users, and you encode them into K independent streams, and then you linear precode them. And what you do at each receiver, at each user, essentially you treat interference as noise. And so user one will decode its own message by treating the interference from other users as noise. This is what typically you would do in 4G, 5G, but you can do the same thing here on DVB S2X, with the difference now that W1, for instance, would not be a message intended only to user one, would be a message transmitted in beam one, for instance, this beam here, and would have to be decoded by 3 users because this message already encapsulates the message of those 3 different users because of the hyperframe structure that you have in those satellite systems. So that's the constraint of the multi-group multicast. But essentially, the precoding approach that you can do across at the antenna feed level to manage the interference between beams is reminiscent of what we have here in SDMA. Now, the important bits here that I want to emphasize is that when you do that, any residual interference that you have at those users here is treated as noise, right? So this is the very important thing that I want to highlight here, and we'll see some in different schemes in a minute. The benefit of that, we know that when you have multiple antennas and you have good knowledge of the CSI, the transmitter, doing this form of processing is actually works quite well, especially in underloaded systems. And you can do this with very low precoder and receiver complexity, since your receiver is just treating interference as noise. And your precoder can have pretty good performance using low complexity techniques like regularized forcing or MMSE precoders or things like that. Now, drawback of this kind of technique is actually it's really suited for underloaded regime, and that's the reason why it works well in cellular system. But satellite systems could be more overloaded, and so in these scenarios, becomes a little bit more difficult with SDMA because essentially you have more users to cope with. It also works well whenever the terms of different users are semi-orthogonal, but the performance may drop quite significantly if the channels becomes a bit more aligned or if the channel strength between users is not similar. And the last drawback is that it's not really robust to imperfect CSIT. And this is a problem that we have in cellular systems, but also in satellite systems. Right. And as I said, it relies on fully clean interference as noise. Now, you can have another techniques that has been popularized in the past decades is called NOMA, or power domain non-orthogonal multiple access, where you use the principle of superposition coding at the transmitter and successive interference cancellations. And so here, for instance, you have 2 users, you create code words for those 2 users and you superpose them in the power domain. And what you do at the receiver is that one of the 2 users will decode the code words of the other user, will perform interference cancellation, and then it will decode its own code words. The other users, on the other hand, will treat the interference from user 1 as noise. So what you see here is that this is a very different strategy compared to what we have with SDMA, because one user here fully decodes the message of another user. So this is very different from the treat interference as noise that we had earlier on. So this has been studied in 5G terrestrial system. There's been a number of papers on this in satellite, but as far as I know, this kind of techniques has not been used in satellite system or implemented in satellite systems yet. But the important message here is, here we don't treat interference as noise. So user 2 is treating interference as noise, but user 1, the strong user, will fully decode interference of the other users. So what that means in a satellite context, it means that if you have this, it means that you may have users here, for instance, users in this beam. What they will do is they will first decode interference, for instance, from other beams, so the message intended to other beams, they will decode that, and then perform SIC, and then decode the message intended to their own beam. So that's the way it could work. Now, we have to be very careful about that when we move to multi-antenna systems. So if you have multi-antenna systems and you perform this form of superposition coding with SIC, and you have here, for instance, this is an example of a cellular system, but the same can apply in the satellite settings, where you have multiple groups, and a given user in the group, what he will do, he will decode the message of all the other users. So if you do that in a multi-antenna settings where you have multiple antennas at the transmitters, what happens with that is that it can lead to actually an inefficient use of the multi-antennas that you have at the transmitter, because it leads to actually a loss in terms of multiplexing gains and degrees of freedom. And at the same time, this comes with actually a complexity increase because you use SIC. And so this is something that we have to be very careful, and this is the reason why we wrote this paper, to draw the attention that multi-antenna NOMA is not necessarily a happy marriage because of these degrees of freedom loss and SIC at the additional cost of an SIC complexity. So we'll see performance of this when we apply this to satellite in a minute. So just to summarize, so NOMA would manage the interference between users or between beams, would work well as long as you have single antenna transmitters. But once you move to multi-antenna systems, or you have multiple antenna feeds, and you can rely on precoding across those multi-antenna feeds, then you may expect a performance loss for the reason that the NOMA will actually not leverage the full degrees of freedom that you have in these multi-antenna settings. And so it's really motivated by single antenna systems, not necessarily by multi-antenna broadcast channels in information theory. So the important bit again here is that we rely on the user to fully decode the message of another user. So we rely on the user in a given beam, for instance, a spot beam, to decode the message that is transmitted in another beam, for instance. Right? So this would lead to a performance loss. Now, a fourth ways of dealing with multi-user interference and multiple users is the so-called rate splitting multiple access, which is a multiple access that is general, flexible, and robust. And it's general because it is a superset of SDMA and NOMA. So you can show that SDMA and NOMA are actually particular instance of that rate splitting framework. It's flexible because it's flexible to any level of interference we have in the system, and is robust because it's robust to imperfect knowledge of the channel state information that we have in the transmitter. It's actually information theoretically optimal in terms of degrees of freedom. And it's motivated by this concept of rate splitting that dates back from the two-user single antenna interference channel by Carlisle and Han Kobayashi 40 years ago. And the idea is to split messages such that we partially treat interference as noise and we partially decode interference. So part of the message will be decoded by the users so that we can partially decode interference, and the other parts will be treated as noise. And by adjusting those parts, essentially we can really bridge the extreme of SDMA and NOMA. So instead of being in a regime where we always treat interference as noise as we have in SDMA, or instead of being in the other regime where we always decode interference, here we actually split the messages so that we can partially decode and partially treat interference as noise. See how it works. We have two messages here, W1 and W2, intended to two users. And so in this case, it's a very generic system. You will see in a minute how it works in satellite. So this is a very generic system, just message and two users. And what we do is that we take those two messages and we split them into two parts. W1 is split into WC1 and WP1. And W2 is split into WC2 and WP2. So this is called the message split. And then we take those two parts and we encode this into a new message, WC, and encode this into stream SC. That's what we call a common stream. On the other hand, those two parts here encoded independently onto two new streams, S1 and S2, that are called private streams. And so we start from two messages intended to two users, and we create three streams, one common stream and one private stream. And then we linear precode that. And so this is what we have here. we have PCSC plus P1S1 plus P2S2. And so the message of user 1, for instance, W1 here, will be carried partially by the stream SC and partially by the stream S1. And what we do at the receiver is that each receiver will decode first SC and will retrieve from SC, will retrieve the part that is interested in. So user 1, for instance, is interested in WC1 that is being carried by SC. And so it will decode SC, will retrieve WC1, then will perform SIC, and then go into S1 and decode S1 and retrieve the other part of message 1, WP1, and then recombine those two into the original message. So this is called rate splitting because the rate of this message W1 now is the sum of two rates. It's the sum of the rate of the private streams that carries part of the message of W1 and is the sum of the rate of this and part of the rate of the common stream, because part of the common stream carries information for user 1 also potentially. And so what we can do with rate splitting is that adjust the content of this split and the collocation to those three streams in order to manage the interference and do a partially decode interference through this common stream and this SIC, and partially treat interference as noise, because whenever user 1 decode S1, it will treat interference from S2 as noise, and equivalently for user 2. Where is SDMA and where is NOMA in this architecture? Well, in SDMA, essentially you turn off this common stream, and so W1 and W2 goes directly into S1, and W2 goes directly into S2. And so you actually turn off the common stream. So here, essentially in your system optimization, if you turn off the common stream, then automatically you end up with two private streams, and W1 will be encoded into S1, W2 will be encoded into S2 automatically. NOMA schemes is obtained as follows. In NOMA, what you do is that you put the message of one of the users into the common streams. So remember what I said here, that one of the users, the user 1 here, decode the message of the other users. So user 1 decode the message of user 2. That means actually user 1 and user 2 will decode the message of user 2. So that means actually, in terms of rate splitting, it's the same as saying that user 2 message now will be a common message. It will be encoded into a common stream so that it will be decoded by both users. And this is what you have in NOMA here. So what you can do is that you can take W2, for instance, that's the message for user 2, and you encode it into the common stream SC. And you take W1, you encode it directly into the stream S1, into a private stream. And so now you have two streams, but those are not the same as here. Here are those two private streams, so any interference between those two is treated as noise. Here, we have a common stream and a private stream, and the common stream here carries the message of user 2, and the private stream here carries the message of user 1. So what we have at the receiver is that both receiver will decode these common streams, and then user 1 will perform SIC and decode the private stream in order to retrieve its own message. And so you see those two actually particular instances of this architecture. And that's the reason why the rate splitting can have actually a performance enhancement over those two schemes, is because those two actually particular instances of that strategy. And you can view this in terms of message to stream mapping here in this table. What you have is essentially three streams and you have two messages. And the question is how you map those two messages to those three streams. In SDMA, you use only the two private streams, so any interference between those two streams will be treated as noise. In NOMA, you put one of the message into a private stream, the other message into a common stream. In rate splitting, you split your messages so that part of the message of user 1 goes into a private stream, part of it goes into the common streams, part of the message of user 2 goes into the private streams, and part of it goes into the common streams. And you adjust the splits. And so you can, in some scenarios, end up doing SDMA, some scenarios you end up doing NOMA, or some other scenarios you end up doing something that is not SDMA or NOMA. Right, so you can show by this that rate splitting is always a superset of those four strategies. Right, so now if you have more than two users, then you can do this strategy here. This is called one-layer rate splitting, where essentially you have now k messages, and from those k messages, you split them and you create one common stream and k private streams. And each receiver here will now decode the common streams and then decode its intended private streams, right? Now, you can apply this into a satellite systems where in satellite, what's going to happen is that the users will have a similar architecture, but the message here have a slightly different meaning. The message here, instead of being a unicast message that is intended to one user, this message W1 now could be actually a multicast message that will be intended to all users within a certain beam. And so this would be the message W1 intended to beam 1, all users in beam 1. This is WK for all, a multicast message intended to all the users in beam K, and so on. Let's see in a minute how that works. So the benefit of rate splitting here is to partially decode interference as noise and partly treat interference as noise, and so therefore bridge those two extremes of NOMA and SDMA. And thanks to that, you always end up with a rate that is better than SDMA and NOMA. And you can show that actually this is really motivated by some fundamental information theoretic results. It's optimal from a DOF perspective when we have perfect CSIT, but that's not very surprising because SDMA is already optimal in that case, but it's also optimal when we have imperfect CSIT. And this is more interesting because it gives us some strong foundations as to why it will be a robust schemes. And then you can show that it copes really well with user deployment, where you have a diversity of channel strengths and directions and CSIT inaccuracy and network loads and so on. But it leads to a higher encoding complexity because now in here you have, instead of encoding K messages into K streams, you encode K messages into K+1 streams. So there's an additional encoding complexity there. So now let's look at how those different multiple access schemes can be implemented in a satellite setting. And I will look at rate splitting here, and I will compare with the SDMA, NOMA, and OMA in different settings. I will look at the multibeam satellite, the multigateway, and then the integrated terrestrial and satellite systems. So when we have a multibeam satellite, and this is really the examples that we had here, this figure that we had here. The question would be how we can use rate splitting into that settings essentially, and how much performance gain that we get over conventional strategy that you have in DVB S2X. So we may have a CSIT uncertainty. That's one issue that we have in satellite. We have this frame-based processing and overloaded regime, and we can have a number of users in each beams that may not be evenly distributed. So we can have some beams actually may contain much more users than other beams. That can happen. And we have a per feed transmit power budget. So all the four characteristics we have to take into account in the design. So let's look at this scenario where we apply this one-layer rate splitting at the satellite level. So we have an example here. We have K users totally across all those different beams. And we have M multicast satellite beams. We have M beams, and those M beams are essentially served by M antenna feeds at the satellites. And so those M antenna feeds creates precoding vectors of dimension M. And this is what we have in the transmit signals that we have the satellite. We have those precoders of this one-layer rate splitting will actually be of dimension M. And so we have, we split the messages. So we have a message of a given group here is to be decoded by those three users in that group. And that message is split into a common and a private parts. A common part that will be encoded into a common streams together with the common parts of the other beams will be encoded into this common stream SC. And then we have the private part of this beam will be encoded into a private streams. And then we perform precoding. and we can calculate the rate of each of those beams, essentially. So the rate of beam M will be obtained by part of the rate will come from contribution of the common streams to its rate, and part of it will come from the fact that we have the private stream that has to be decoded by all those users in that beam. So we have a multi-group multicast, and the goal will be to try to maximize the minimum rate among all the users. So what you have here is that you have essentially a multicast stream SM that has to be decoded by all the users within that specific beam. And this is the reason why you have this minimum here. Now, what is the rate at which we transmit this common stream? Well, this is given by this. So this is essentially the contribution of, or the portion of the rate of the common stream that is really, that really benefits beam M. And so the sum over all those beams essentially gives you the total rate of the common stream. And the common stream, SC, has to be decoded by all the users in the network. So that means actually all the users, user 1 to user k, will have to decode that. And that means actually this is the rate that actually is supportable by user 1. This is the rate supportable by user k. And we have to transmit this common stream at a rate that is supportable by all those k users. And you can calculate those rates as a function of the precoder, and then you can optimize this. And so what you can do is that you can find the split of the messages. So this is captured by C, which is a vector of all those CM, and the precoders, this common and private rate, in order to maximize the minimum rate that you have among all the users, essentially. And you have a rate constraint that is the achievability of the common streams. You have a per antenna feed power constraints. And you can solve this using convex optimizations. And so what you get here is an example where you have 7 beams and you have 14 users and 2 users per beams. And you have here the minimum rate that is achieved. So we try to maximize the minimum rate among all those 14 users as a function of the per antenna feed power at the satellite. And what you have here in green is when you have this 4-color frequency reuse. And so you see that actually this does not perform so well. And the reason for this is because obviously you have a lot of spectral efficiency because you have to of this orthogonalization of the frequency spectrum. As you move to the red and the blue lines, what we have is RS is rate splitting, or RSMA, one lane rate splitting, and the blue one is SDMA. Here it's called no rate splitting. It essentially means SDMA, so it's conventional multi-user linear precoding, where you treat any residual interference as noise, but you optimize the precoder so that you manage the interbeam interference. And you have different curves here depending on the quality of the CSI that we have at the transmitter. And so what you see is that here the rate splitting outperforms, in red always outperforms the blue curve. Essentially, the presence of the common stream enables you to really manage the interference between beams more efficiently. And the gain actually becomes a bit larger as the CSIT quality decreases. And this is what you can see here. As the CSIT quality decreases, the gain of rate splittings over SDMA or multi-user linear precoding is actually increasing, relatively speaking. Right. So this is another scenario here where we look at the per antenna feed constraint versus a total power constraint. And what we show here is actually the per antenna constraint is not really a main issue. Once you optimize the systems, you can come quite close to what you would get with a total power constraint. Right. Another scenario is when you have hotspots. So this is a scenario where you still have M beams and 14 users, but now you don't have 2 users per beams. You actually have in this configuration, you have 8 users in one beam, and then you have 1 user in all the other beams. So you have very uneven distribution of users. And what that shows here is that the pink curve here is the rate splitting, outperforms all the other schemes here. No rate splitting, for instance, is there. Whether you have uniform user distributions or whether you have hotspot scenarios, in both cases, the rate splitting outperforms the other multi-user or multiple access schemes because of this ability to, again, manage the interference by partially treating it as noise and partially decoding it. So this was about how to manage interbeam interference. Then we can move to scenarios where we have now multiple gateways. So what that means is that the one of the drawbacks when we have this scenario here is that, let me take the original figure when you see the gateway, is that if you have many beams here, you actually need very high throughput over the feed link in order to serve all those different beams. And in some scenarios, you actually may be bandwidth limited on the feeder links. And so what you would like to do then is to use multiple gateways at different geographical locations. And those gateways are equipped with very directive antennas. And then you reuse the bandwidth or the frequencies across those different gateways. So this is the multi-gateway architecture. And this architecture leads to other challenges. So now we have essentially this feeder link spectrum that is now reused across gateways here. So all those different gateways will actually direct the transmission towards the satellite and all operate on the same frequencies. Now those gateways, gateway 1 will now communicate not with all the antenna feeds from the satellite, but a subset of them. So the total number of antenna feeds now will be divided into groups, into clusters. And so the first cluster here will be actually the antenna feeds that is intended to gateway 1. Gateway L will have a subset of all those antenna feeds, and so on. And the issue with having those multiple gateways is that now you introduce inter-gateway interference. And so indeed, this gateway will leak towards the antenna feeds of another gateway, which itself will leak towards the beams of other users, or other beams that's on intended beam clusters. And so what we can do, we need to tackle two things here. We need to tackle the interbeam interference that we have on the user link, and then we need to tackle the feeder link interference that we have here, this inter-gateway interference. And to do that, we're going to look at multiple access schemes on the downlink here, and again, looking at rate splitting and the other schemes. And here on the feeder link, what we're going to look at is how we can use onboard processing, which is essentially a filter that you have at each of those antenna feed here, that enables you to try to manage the interference that you experience from the other gateways. Right, so each gateway can perform rate splitting. So you can implement rate splitting here, and each of those gateways will implement rate splitting, and the rate splitting will be intended essentially to manage the interference that you have here within all those beams in this beam cluster. Right, so the way the architecture here of this rate splitting is the same as what we had before. We have WM would be the message, the multicast message intended to beam M. And this rate splitting will try to manage the essentially interference between multiple beams in a given clusters. And so you actually split those messages into common parts and private parts, and then each of the user will perform the SIC and then decode the private stream, as I have explained before. Right. So let's look at an example here. We have M beams equal to 9 in these scenarios, and we have 3 gateways. So gateway green, for instance, will essentially serve those 3 beams. So we'll try to manage, using rate splitting, we'll try to manage the interference that we have among those 3 beams. And then gateway 2 will actually take care of those other 3 beams in yellow here, and we'll use rate splitting or other multiple access to manage the interference between those beams there. And then the interference that you have now between those two different clusters of beams would have to be managed. And one way of doing that is to do this onboard processing through this filter here at the satellite. And so we can design this, design the onboard processing, and we can design the rate splitting in each of those clusters on each of those gateways. And what we end up with is the results that we have here. So this is, we have 3 different multiple access, rate splitting, SDMA, and NOMA here. And what you observe is that the rate splitting in pink, and you have 2 different cases. You have the case where you have no onboard processing, and you have the case where you have onboard processing. And so what you see is that the best performance here is obtained by doing rate splitting in each of those clusters coupled with onboard processing. So that would give you quite a bit of gain over doing SDMA with onboard processing. You have this gain here essentially comes from the fact that you manage the interference between the beams thanks to the rate splitting versus the SDMA. And then you have the gain of this OBP versus the rest here comes from the fact that you have the gain of the OBP that manage the inter-cluster interference or inter-gateway interference essentially. So the combination of OBP and rate splitting is what gives you the full performance enhancements here. So another scenario here is when we have hotspots. So in this scenario here, we had 2 users in each of those beams. So you can have again a scenario where you have hotspots, same as before. You can have an uneven distribution of users across the beams. And here the observation is the same as what we had before, essentially that if you do rate splitting, you're going to have an OBP, you're going to get the best performance over doing no OBP or over doing SDMA or NOMA schemes. Right. So that's the main message that we have here. And then you can scale up the number of beams, the number of gateways. So here's an example where we have 21 beams, we have 7 gateways, and we have 2 users per beams. And again, the same observations are obtained. And so you can argue there is a trade-off in terms of complexity between having many gateways and each gateway serving only 1 beam, or having only 1 gateway that has to serve many beams. You have a trade-off here between performance and complexity. And if you have a mixture of both two, essentially, you can tackle this using a combination of multiple access on the user link and onboard processing on the feeder link. Right. Another scenario is the satellite-terrestrial integrated networks. And so here we have scenarios where we have a multibeam, multicast transmission, as we have seen before. And in each of the beams, we now have a cellular system, a cellular network, that serves also terrestrial users. And so we have satellite users here that typically may not be in the covered area of the terrestrial network. And those those terrestrial users here would potentially receive the interference from the satellite transmissions. And so the question here is that if we have some form of cooperation or coordination among satellite and the terrestrial network, how much performance enhancement can we get? And so this is the question that we try to address here, is whether we should do coordination or cooperation. And this is a little bit reminiscent of what we have in cellular systems also, for instance, what we have in coordinated multi-points. You can do a coordinate scheme to manage the interference, and we have multiple forms of interference here. We have the interbeam interference of the satellite. We have the intracell interference among the cellular users. And then we have the interference between the cellular and the satellite systems. And so we have a coordination means that you share the CSI of all those users, so the satellite users and the terrestrial user, you share the CSI to a gateway. And this gateway will decide how to design the precoders of your favorite multiple access schemes. be it RSMA, SDMA, NOMA, whatever, at the satellite and at the base station of the cellular network. But in this case, only the CSI would be here. And then you have the cooperative schemes that says, well, we're going to share the CSI of all those users, but we're also going to share the data of all those users back to the gateway. And then the antenna feeds of the satellites and the antennas of the terrestrial user will act essentially as a giant array and perform a form of joint transmissions across all those antennas to manage the interference. And there again, you can use your favorite multiple access schemes, be it SDMA, NOMA, or RSMA. So this is what we look at here. We have 16 antennas at the terrestrial network, so the cellular base station. We have 4 users at 4 terrestrial users. We have 3 beams at the satellites, and we have 6 satellite users, so 2 users actually per beam in this case. And you have in the dashed lines are when you do cooperation using rate splitting multiple access. The solid lines is when you do coordination, but still using rate splitting multiple access. And what you see is that you have here those 3 lines obtained with different power level at the satellites, and you have the x-axis is the power level at the terrestrial base station. And so if the terrestrial base station has a very weak power level, what happens is that you're limited by the rate of the terrestrial users. And essentially what happens is that you end up with essentially a minimum rate that actually can be quite low if you do coordination. If you do cooperation, you can get significant performance enhancement. And as the power of the terrestrial base station increase, at some point, the coordination tends toward the performance that you achieve with the cooperation. And then you can compare what kind of multiple access you can have. So you can have, for instance, when you do coordinations, you could have rate splitting at the satellite and rate splitting at the base station, the Terrace base station. Or you could do rate splitting at the satellite and SDMA at the base stations, or inversely, or you can do NOMA. And when you do cooperation, you could do cooperation using SDMA, or you could do cooperation using RSMA. What that shows here is that the best performance you would get is to do cooperation using RSMA. And if you do coordination, when you have these solid lines, blue lines with the square, this is the best performance you would get when you do coordination using RSMA at both satellite and terrestrial. And if you do SDMA on one of those links, for instance, on the base station links, then you incur some performance loss and further performance loss if you do SDMA on the satellite instead of doing it at the base station. So you see the yellow one is lower than the red one. So it seems to imply that it's better to do rate splitting at the satellite than the base station. You would end up with more performance enhancement by doing it at the satellite and the base station. And that's the reason, is because it's an overloaded systems, and that's subject to more interbeam interference. But so the baselines that you can get, rate splitting gives you the best performance, and as you increase PT, the performance of coordination tends towards the cooperation. And then you have 2 baselines here of naive baseline. The first one is you separate the design of the satellite and the base station. They still operate on the same frequencies, but the design of the rate splitting, the precoders are currently done independently from each other. And that ends up with relatively poor performance in some regime. And the other case, baseline 2 here, is when you do rate splitting plus OMA. So that means actually the terrestrial and both satellite and terrestrial use rate splitting, multiple access, but the satellites and terrestrials operate on 2 orthogonal frequencies. And that leads towards performance loss because of spectral efficiency loss of the reuse factor, essentially. Right, so here, similar observation. This is what happens when you increase the number of antennas at the terrestrial base stations. And what that means is essentially, indeed, the minimum rate increases, and you actually end up with reaching the cooperation performance a bit more quickly than when you have a lower number of antennas, which is quite natural. So this was for perfect CSIT, and this is here for imperfect CSIT. And the imperfect CSIT here is in the settings where we have some imperfections on the face of the elements of our channel vectors. Essentially, we don't know perfectly the phase of those elements. We have a certain variance on this phase. And as the variance increases, you see that the performance simply drops, whether it's for coordination or for cooperation in the dashed lines or the solid lines, both of them performance drops. And if you compare the left figure with the right figure, you have left is rate splitting, and the right one is SDMA, and you see that the left minimum rate is higher than the right one, showing again that if you have rate splitting would manage the interference more efficiently than SDMA, especially also when you have imperfect knowledge of the CSI on the satellite links. Right. With this now, you can assume that you have infinite block lengths and Gaussian signaling. Now you can do link level simulation to really understand how much performance you would get with finite block lengths and the real error correcting codes, for instance, polar codes, and real, realistic modulations, for instance, QPSK 16 QAM, 64 QAM, and so on. So you can implement these link level simulations where you have the method splits, you have the polar encoder, you have interleaver, you do adaptive modulation encoding, where your adaptive modulation encoding decides your coding rate and your modulation for the common streams and the private streams. And this is fed, the decision is based on the optimization that we have from the previous slides. And then you need potentially a backup in order to cope with any errors that you may have at the receiver when you perform SIC, where you may have actually imperfect SIC because of your finite length polar codes. So you may have error propagation that needs to be taken care of when you do the adaptive modulations and encoding. And then if you do that, and if you apply this to these multi-beam satellite systems, this is the actual maximum throughput performance that you get. So this is not only rates. You have the rate, the solid lines here is what you get when you have Shannon bounds. So this is with Gaussian signaling and infinite block lengths. And the dashed line is what you get when you have an actual finite constellation with actually SIC error propagation and finite block lengths polar codes. In the scenarios where you have 7 beams and 14 users, and what you see is that the gain of rate splitting that we had with Gaussian signaling is still there. It still appears with finite block length, and actually, relatively speaking, the gain is even higher. And you can see the significant performance you get with rate splitting in red versus SDMA in blue. You save quite a lot of per antenna power to reach a given level of throughput, for instance, 1 bits per second per hertz. So with this, I will conclude. And what I want to highlight here is that there's some interesting signal processing challenges for satellite communications. One of the objectives is obviously to achieve higher throughputs, and higher throughputs means dealing with 2 forms of interference, so potentially 3 forms of interference. Interbeam interference that you have that comes from these multi-beam architectures of satellite. The intergateway interference that comes from the fact that you have a reuse of these feeder link spectrums and you use multiple gateways, and potentially you can have another form of interference that comes when you have the integration of satellite and terrestrial networks. And all those 3 forms of interference actually requires some really special attentions on how we actually manage the interference efficiently using some more advanced signal processing. And other issues that I have not mentioned, Doppler is obviously an important problem to consider when you have LEO. So the settings I considered here were mainly geostationary, but there is lots of issues that arise when you look at LEO. Other issue that may be interesting to look at is obviously how you manage the interference using multi-antenna and multi-user signal processing when you have a massive number of multi-beams. So instead of having 14 beams, like I had, for instance, or 7 beams and 14 users, you may have hundreds of thousands of beams. And each of those beams may serve multiple users. And then you may have the mega constellation also, where actually those LEO or very low Earth orbits satellites, you're going to have so many of them that they may also interfere quite a lot with each other and with the terrestrial network. And there may be some needs to actually have more efficient signal processing there. The last one I have not talked about, but there is some papers in the past few months have come up, is how you actually can also integrate communication and remote sensing at the satellite level. And this leads to an additional problem of interference management, is the interference between communication and radar or remote sensing. So on top of the interference that I mentioned already. And so for all those ones, what I showed is that you need to come up with some multi-beam, multiple access interference management strategy that is robust and flexible. And in that context, rate splitting multiple access fits quite nicely because it's really partially decode interference, partially treat interference as noise, and has been shown in various settings that is quite efficient in dealing with interbeam, intergateway, inter-satellite and terrestrial network interference, and have significant gains over other techniques, especially because of the overloaded regime that you experience in satellite communications. So with this, I will stop here, and I will be very happy to have further discussions or answer any questions that you may have.
Okay. Thank you very much, Bruno, for such a very interesting talk. I don't know if any of the attenders have any question. Can write it down into the chat or okay. Can you read the? I mean, Houda Chi is asking about what is the problem on mobility.
So, I mean, you may have the mobility I mentioned earlier on. You can think of this one here. Right. So you may have latency mobility here. I mean, if you have a user, imagine you have a geostationary satellites, and you have a user is moving at a certain speed. Obviously, his channels will change a bit, right? Even though it's line of sight, it will change a bit. And because of the long latency that you have on the satellite link, this round-trip delay of 500 milliseconds, this can lead to actually quite significant change of the channel for over 500 milliseconds. Similarly, if you have LEO satellite, would be even worse because it's not only the mobile is using, but you have the satellite is evolving very quickly. And so within 25 milliseconds, the channels may change quite a bit as well. This is the first issue. The second issue is the whole Doppler when you have mobility of the satellite, because then you have the whole problem of no synchronization that comes into play, right? So this is actually something that is well understood, is a major issue in LEO, but it's probably something that will come back as you move to even lower Earth orbits and you have even a higher Doppler.
Okay, I think the question is solved. So another question, is from Ana Garcia. When cooperation between terrestrial and non-terrestrial network, the last part of the talk, what information need to be shared? I mean, it is the signaling overhead. This overhead is feasible, or that is too much.
So indeed, there are many issues there, practical problem, and for those who are familiar with joint transmission or coordinated multi-point cellular systems, you have similar problems here. So essentially here you need to have, gateway has a lot of decision power. Essentially, all the computing power is there and has to decide, you know, the precoding that you have, the satellite and the multiple access there, if you do rate splitting, and at the terrestrial base stations. And to do that, you need to feed back all the CSI all the way to the gateway when you do coordination. When you do cooperation, is even more than that. You need to feed back not only the CSI, but also the actual messages. You need to feed back all the way to the gateway, because those messages will have to be then transmitted from the satellite and from the terrestrial. So this leads to a certain amount of overhead on those backhaul link. And so this is a little bit reminiscent of all these issues that you have in C-RAN also, you know, when you have front hauls and you have limited capacity on those front hauls, you're going to have similar problems here, but probably even more significant, because you're going to have the link, the backhaul or the front haul between the gateway and the terrestrial, but then you have the over-the-air here, the satellite links also, that's going to have to cope with all those demands. So this is one issue. Another issue is obviously the synchronization. I did not mention here, assume everything is perfectly synchronized, but we know very well that the latency between the satellite to the ground here, to the Earth, is very different than the latency between a terrestrial base station to its own users. So maintaining synchronization, time and frequency synchronization, when you do joint transmission and precoding across all those antenna elements, satellite and terrestrial, is very, very challenging. Will be much more challenging than what we have in terrestrial joint transmission, for instance. So lots of practical problems to take care of.
Yeah, and I is asking that it's good to know the upper bounds for this, just to know what are the limits just to
yes.
can be reached.
So I think what would be interesting in this setting to make it more realistic is now try to bring it, you know, actually constraints on the backhaul, on those links between the gateway and the terrestrial base stations. There you need to have maybe some constraints on the maximum throughput you can afford. You may have also additional constraint on the feeder link here. And this would change a little bit the way you do the interference management. So this is something a bit reminiscent. We have this in C-RAN with front haul, and there are different ways of doing rate splitting multiple access, for instance, how you split the messages. I think something similar can be done there in the context of integrated satellite and terrestrial.
Okay, thanks. And it's somehow related to this question. I received a question from a colleague that have left earlier the talk, and it's about, it is possible to, I mean, I guess the answer is yes, but it's possible to implement this rate splitting in multi-satellite. Means not having several satellites and sharing everything just to this rate splitting for different satellites. It's possible? I guess the answer is yes.
So when you say multiple satellites, so you mean, for instance, here you're going to have one satellite. Yeah, so you would probably not have GEO in that case. You would have LEO.
No, it's not GEO. Yeah,
yeah, you would have multiple LEOs. I mean, you could have multiple scenarios here. You could have one LEO satellite has to communicate with other LEO satellites. And you may have interference between those LEO satellites. And so there you may have interference management problem. And so you can do all those kind of multiple access schemes that we're familiar with in communication theory. You can do this in a satellite, inter-satellite links. That would be possible. Then you could have the other problem, which is you have multiple LEO satellites that serves, you know, maybe the same users on the ground. So their beam essentially is overlapping. And then you could have cooperation among those multiple satellites to beam on the ground. And there you could have rate splitting, you could have SDMA and so on. I think this is all possible.
Yeah, even you can have it, MEO, this medium or satellites covering larger area, and then having a constellation in LEO just for increasing capacity. So
that's right. You can have a hierarchy of, you know, satellites
Yeah.
And the question is how you manage the interference. So that's the key question. So the question is, in those multiple access, I don't think it's about, you know, whether it's orthogonal, non-orthogonal. That's not really the problem, because lots of those multiple access schemes are inherently already non-orthogonal. But the question is how you really manage the interference, and this is where the difference in performance comes from. But I think it's possible. Yes, what you mentioned.
Yeah, I mean, the most challenging part in this scenario is that when cooperation or coordinated with terrestrial network, the satellite is on the top. I mean, it's covering this area. But when you have several satellites, you need to somehow have in the Earth some gateway or some intermediate station just for this, for making possible this cooperation, because otherwise they will not communicate. I mean, unless you are doing some kind of inter-satellite link or something like that, which could be complicated in some scenarios.
Right.
Okay. If is there any other question from the audience?
Bruno, can I ask a question, if I may, please?
Please.
What do you think the role of like AI-based techniques to solve this problem? I mean, you mentioned the main problem is interference, but this whole package of you know, multi-beam, multi-access management, considering the interference problem also. So what do you think the role of, would it be possible to consider AI-based techniques to aid in designing these multi-access interference management schemes?
Well, I think, you know, AI has a lot of advantages, and obviously same for terrestrial, that there are lots of areas where potentially you could use it. I think we have to see how much gain you would get over this kind of techniques like here. So in the scenario that I mentioned, if you apply AI to solve the optimization problem, I'm not sure you would have much benefit, in the sense that those optimization problems can be solved already in relatively efficient way, at least in terms of, we don't know what's the global optimum, but we are quite convinced actually the global optimum is not far away from the local optimum that we reach. So if you use AI to try to improve on the performance, maybe you will not get so much benefit in that setting, given the assumption that we have. If you use AI to reduce the complexity of the design, there could be some benefits, especially if you go to those very large scale systems where the optimization becomes very complicated. Now, there are lots of assumptions in the work here, right? And some of the assumption is obviously that everything is linear. So we have linear systems. We know that in satellites, the HPA is highly nonlinear. So there is a lot of work there on use AI and machine learning to try to cope with nonlinearity. Whether you have terrestrial systems or you can have this on satellite system as well. And there your resource allocation could change a bit because of the nonlinearity that you bring into the picture. I'm pretty sure that AI will have a role to play in these kind of settings, whether it will be purely at the physical layer or will be at higher layer. It's a bit difficult to say. So for instance, we have done work on AI for rate splittings, where we do all the successive interference cancellations. We actually replace this by specific, or the detection part, we replace this by essentially machine learning techniques. Right. And so this has some benefits in some scenarios where you don't know the channels well, because you have nonlinear boundaries that you can really enable using AI techniques. So I think there are definitely pockets where actually a combination of classical signal processing and AI-based techniques could be beneficial.
Thank you very much. Thank you.
Yeah, we have some other question from the audience. Another one is, how can we manage beam coverage with multiple LEO satellite? And why a few users, only 2 users per beam?
How can we manage beam coverage with multiple LEO satellites? Well, I think the trajectories of those satellites, are designed so that you maximize the coverage essentially. But because you may have many of them, it's very likely that there may be some overlap between the beams created by those satellites. That depends really on the density that you have and how the system is designed. But I can imagine that it is possible that you have some form of coordination that is possible between multiple LEO and the strength of those. So the cooperation or coordination among those different LEOs would help you to increase the signal strength on the grounds, and so therefore also increase the quality of service. Now, why we use 2 users? No specific reason. We have to start somewhere. You could have more than this. So sometimes I think we have more than 2 users. I mean, especially when you do the hotspot where we have 8 users in one beam. But no specific reasons. The more you increase the number of users, the more you increase the number of beams, of course, the longer the optimization takes. But you could take a larger number of users, yeah. So here in this example, actually, we take long phase simulate with many more users. You see, so here we have m beams. M is equal to so the number of beams is equal to 9, but we have the number of users per group is actually well beyond 2. In general, because you do max min fair, so you maximize the minimum rate. As you increase the number of users per group or per beam, essentially you have the rate decreases, which is natural because your message have to be decoded by all the users. But you could use other metrics. You could use sum rate. You could use other metrics.
Okay, thank you. And another question is about complexity and issues about, challenges on implementation, complexity, delay, and how is this kind of issues?
I mean, if I take this, so the OBP obviously leads to a different complexity because you need to do the processing at the satellite. So if you don't have OBP, it's simpler because essentially you end up with a diagonal matrix here. So obviously this is one aspect. The whole concept, the whole SIC thing that you have in RSMA or NOMA obviously increase the complexity at the receivers. But when you look at rate splitting here, the schemes that we use is 1 layer rate splitting. You have essentially only one SIC at the receiver. So the complexity is not really at the satellite part, is more at the receiver side. But one SIC with modern systems, I think is very much feasible. If you think about 4G, 4G MIMO was already designed with one SIC, in mind. So I think nowadays doing one SIC, I don't think is such a huge complexity. I think it's very much feasible. I think what is very practical in a way is, I think this multi-beam satellite we're using rate splitting is something that is, practical as you move towards these more complex scenarios with integrated cellular and satellites. The complexity there is huge, right? Especially if you want to do this full cooperation, the complexity is quite enormous. Yes, that's what I can say. But I think if you do academic research, you have to be mindful of complexity. At the same time, you don't have to be bounded by complexity because complexity is something that evolves over time. What you cannot afford today is something you can afford tomorrow. So But yeah.
Okay. Thank you, bro.
And
I think there's
not
question by Dr. Madhu, maybe just a last one in the interest of time. That polar codes are being considered for 5G. Can I use the above codes for 6G and 7G channel code?
Sorry, polar code I use for 5G. Yes, can I use what?
Can I use the above code for 6G and 7G as channel code? I'm not exactly sure how this is.
Well, I mean, those codes evolve as time goes by, but I mean, we had turbo in 4G, and then it has changed over time to LDPC. Now we have polar code. So, I mean, I think polar code is used for control channels in 5G. It's very likely that in 6G there may be some enhancement on those codes. The reason why we use polar codes here is we could have used other codes. We could have used turbo or LDPC. The polar code doesn't have any specificities here in terms of, you know, the combination of rate splitting, and rate splitting can be used with any forms of error correcting codes essentially. But is a more recent code, so that's the reason why we essentially use that. But you can use other type of codes. But I'm sure there would be enhancement in 6G on the coding schemes. Yeah.
Oh, okay. And one curiosity, more than a question, when you talk about this rate splitting, this coordination and stuff, how do you, let's say, you have two parts. One part is when you make this adapting and modulation and coding, when you apply these kind of things. For the common part, how do you decide which AMC for choosing? Because you know, for when you do to a specific user, is simple. I mean, you adapt to the channel for this user. But in the common part, you are adapting for the whole number of users, and probably
Yes.
it takes effort on the global performance.
So you see what we have here is so you have R1, R2, C1, C2. So the sum of C1 plus C2 is essentially the rate at which you transmit the common stream. And so C1 is a portion of the rate of the common stream that is actually intended to use a 1, and C2 is the portion of the rate that is intended to use a 2. What is important in the common stream is that you fix the rate at which you transmit such that is decodable by all the users. So that's something that is quite important. Now, whether you split you know, both users' message or only one user, that really depends on the scheme. So and the objective function. So here we use the max-min fair. So you try to maximize the minimum rate among all those users. And this is a scenario where, if I take the formulation here, this is a scenario where it becomes very helpful to actually split the message of each beam, because what you want to maximize the sum of those two, the private part and the common part. That's the sum, that's the total rate of beam M. And it's very likely that what's happening is that each beam will actually benefit in a way from splitting its multicast message. But if I use other metrics, not all beams or not all users will have to split the message. That may depend on the objective function. And some way it would be a case where actually you don't always need to split multiple users. So that depends really on the objective. Now, once you have that, then you can bring this solution into the link level simulations here. But obviously the problem is that you will have some packets will be wrongly decoded. And so once you have those rates, whether they're common or private, you need to map these rates to a certain modulation encoding rate. And so you can do this by mapping to the closest, spectral efficiency that you get with a certain modulation encoding rate. But you have to be mindful of the fact that you may have some errors on the decoding, and so you want to aim at certain percentage of, errors. For instance, 10% of packets are wrongly decoded, for instance. And if you aim at this, then you can adjust your backoff for the private and the common, according to that target. But that's a little bit heuristic, as you know, for anyone who has done link level simulations, and especially when you have limited block lengths like this, you have to play a little bit with this link adaptation in order to maximize your throughput. Yes, but this is a bit similar to what we have in conventional systems. You have in 4G, 5G. You would have to do that. But here, additionally, you have the common stream that have to be decoded by multiple users. So there are things I have not talked about here, right? The whole notion of RBDIQ, for instance, I have not discussed. And that's something that is also a common question I receive often that needs to be addressed. So here we don't assume RBDIQ, you just have either your packet is correctly decoded or not. So your throughput capture essentially the spectral efficiency of your transmission and also the 1 minus the percentage of error that you have.
Okay, thank you. I don't know if there are any other question. Okay, I think yeah, can stop recording. And so thank you again, Bruno, for joining us in this very interesting talk. And the discussion has been also interesting. So I think it has been a success.
Thank you very much, Victor and Numan, for
thank you so much. Yeah, absolutely. Yeah, very pleased to have you. It was very exciting and informative.